Okay. So again, how's everyone feeling today? Okay, a lot of energy. Okay. So we're gonna go through the first half of the year, and it's gonna be like a quick overview. I wouldn't necessarily copy every single thing down because all of this should already be in your notes. I would just kind of like watch and wake up to it, and then if there's something that you're like, oh man, I need to go back and study that, maybe just make a note of that. But if you're trying to copy everything down, you might not be able to keep up. And also, I'm recording this so that if there's anything that you feel like, oh, you really want to go back, you just go back and look at the recording. So I would just sit back and relax and just open up your mind, enjoy the show. Okay, please make sure your cell phones are turned off. Just kidding. Like a movie. All right. So first thing we're going to do is look at straight line motion. There are key formulas that you just have to know, like the back of your hand. And that is V bar equals X over T. A equals delta V over T, where delta V is equal to VF minus VI. A replacement for this, it's really the same formula. If you substitute that VF minus VI in for the delta V and then you solve for VF, you get VF equals VI plus A times T. And then for uniform accelerated motion, if you take the initial velocity plus the final velocity and divide by 2, you get the average velocity. And then, of course, the great displacement formula. And then the no time formula. So these formulas here, are for uniformly accelerated motion only. Once you have this down, the other thing besides using these formulas you want to be able to do is graph the motion. And there's basically like 9 key graphs that you just want to know, like the back of your hand. 3 for standing still, 3 for uniform motion, and 3 for uniformly accelerated motion. So if the object is standing still, there's going to be 3 motion graphs. And then if the object is moving uniformly, and then if you have uniformly accelerated motion. So 3 graphs. Displacement versus time. Velocity versus time. Acceleration versus time. And then displacement versus time. Velocity versus time. Acceleration versus time. And then same 3 So if an object is standing still, they could be standing still anywhere. They could be standing still on the 1 meter mark. They could be standing still on the 2 meter mark. I'm going to have the object standing still on the 5 meter mark. And then 1 second later, they're still on the 5-meter mark. 1 second later, they're still on the 5-meter mark. 1 second later, they're still on the 5-meter mark. So it would just be a straight line wherever they're positioned. Sometimes this is referred to as position time graph. Okay. Now, of course, if they're standing still, their velocity is 0 the whole time. And acceleration is the change in velocity over time. And since their velocity is not changing, their acceleration is going to be 0. Now, with uniform motion, the object keeps covering the same amount of distance each time period. So maybe in 1 second, the object goes 2 meters. And then in the next second, they go another 2 meters, so they're 4 meters away. And then in the next second, they go another 2 meters, so they're 6 meters away. So you end up getting a straight line looking like this. And basically, the slope of that line ends up telling you how fast the object is going. So whatever that slope is, in the example I just stated, was like 2 meters per second. You know, that turns out to be what the velocity is here. So for uniform motion, velocity time graph, it's just a straight line going straight across. Now, since the velocity is still not changing, once again, the acceleration time graph is just 0 because it's 0 acceleration. This should be a straight line right here. Now, notice the slope of this line right here is equal to 0. Well, turns out that's what the acceleration is over here. 0. So basically, things to remember, the slope of the position time graph gives you the velocity. The slope of the velocity time graph gives you the acceleration. Now, with uniformly accelerated motion, the acceleration is constant. This is tricky because you have uniform motion here, and then uniformly accelerated. And both of them have that word uniform in it, but you have to realize uniformly accelerated means that the object is speeding up. It's just that it speeds up by the same amount each second. So basically, another way of saying uniformly accelerated motion is constant acceleration, whereas uniform motion is constant velocity. Uniformly accelerated motion is constant acceleration. Free-fall motion is an example of uniform accelerated motion because the acceleration is always the same, -10 meters per second squared. Here, we're just going to make the object have some positive constant acceleration, so it's always the same number. And therefore, the velocity keeps on increasing the same amount. This should be a straight line right here. Each second. And then the position time graph ends up looking like a half a parabola where it's curved up. So, curved up. Now, another thing you need to know is if you draw a tangent line on the displacement time graph, a tangent line just skims the curve at one point. If you find the slope of that tangent line, the slope of the tangent line at that particular time, right here, well, that will tell you how fast the object is going right there. That would tell you the value of the velocity right there. So the slope of the tangent line equals the instantaneous speed at the point where the tangent line was drawn. Running out of room over there, I'm just squeezing it. The instantaneous. At that point right there. So those are the 9 motion graphs. You want to know like the back of your hand. You know, memorize them, and better yet, understand them. But be careful, because a big mistake is people don't look at the axes, and they'll be given a graph like this and be asked, what kind of motion is this? And if you can answer that question, what kind of motion am I showing? Then you fail to recognize you don't know what kind of motion this is until the axes are identified. So it's so important to look at the axes. Because if this was a distance time graph, then that graph there shows a uniform motion. If this was a velocity time graph, then this shows uniformly accelerated motion. So make sure you pay attention to what's on that y-axis before you decide what kind of motion you're dealing with. The last thing you need to remember is if you calculate the area underneath the curve of the velocity time graph, that ends up telling you the displacement. So if you calculate this area, like let's say right in here, that area equals the total displacement so far. So whatever that area is, it would be the value right over here, what the total displacement is at that time. So equals, so fun facts to remember: the slope of the position time graph gives you the velocity. The slope of the velocity time graph gives you the acceleration. The area underneath the curve of the velocity time graph gives you the total displacement. Those are the 3 fun facts to remember. And before we leave straight line motion, one thing I want to point out, a popular mistake students make is they tend to forget that this average velocity right here and this change in velocity, those are 2 separate things. Those are not equal to each other. So basically, average velocity does not equal change in velocity. So you can't just take and go like this. Average velocity equals distance over time, and then once you get that average velocity, say acceleration equals change in velocity over time, and then throw that value in for there. Because these 2 are not equal. So this is a big no-no. If you looked at the numbers, like say an object had a velocity of 12 meters per second, and then they were going 13 meters per second, and then they were going 16 meters per second. Well, the average velocity of those 2, you would take the initial plus the final and divide by 2, and if you did that, obviously you would get 14 meters per second. But the change in velocity would be the final velocity minus the initial velocity, and of course that would be 16 minus 12, so that would be 4 meters per second. Notice, they're not equal. So watch out for that mistake right there where you make that substitution. Don't do that. Okay, so that wraps up good old straight line motion. What came next were vectors. And basically what you need to remember is if you have an object and you have a 10 Newton force and a 4 Newton force acting in the same direction. If they're acting in the same direction, right in there, that angle is 0 degrees. If the angle between them is 0 degrees, then to get the resultant, which is also called the net force, you simply add them together and you get 14 newtons. So when the two forces are going in the same direction, you add them together. If the two forces are going in the opposite direction, and the angle between them is 100 degrees, then the resultant force, which is equal to the net force, would be equal to 6 newtons. You subtract them. And then finally, if you have the two original forces at a right angle, 10 newtons, 4 newtons, and the angle between them is 90 degrees. If you want to find the resultant, and the original vectors are at 90 degrees to each other, you have to put them in head to tail form. Where you draw one vector, and then at the head of that vector, you add the next vector, and then you draw the resultant from the original starting point, and then it headbutts the last vector added. So this here would be the resultant, which also is equal to the net force. And then you'd also have to find the magnitude and the direction. Basically, in this case, it would be 10 squared plus 4 squared, so it would be the square root of 10 squared plus 4 squared, which would be 100 square root of 116, whatever that comes out to. And then you'd have to use inverse tangent to get theta. So basically, the tangent of theta equals opposite over adjacent. So the tangent of theta would equal 4 newtons over 10 newtons. And then you take the inverse tangent and you get your angle. So vectors, if they're both going the same way, you simply add them up to get the resultant, also known as the net force. If they're going the opposite direction, you subtract them. And if they're going at right angles, then you have to put them in head to tail form. Now, sometimes you'll be given 3 forces, like 1 newton, 2 newtons, and 3 newtons, and you'll be asked, is it possible for these 3 to be arranged in some way or another, where the 3 forces are in equilibrium at any old 3 angles? Well, what you have to do is look at any 2 of them and ask yourself, what's the biggest they could add up to? Well, the biggest they could add up to is this first case here, where they're going the same direction and you just add them up. So the biggest they could add up to is, 3 newtons. The smallest they could add up to is 1 newton. And then you ask yourself, hey, would it be possible for them to balance out that 3rd newton? And the answer is yes, it would be possible. Sometimes the answer is no, though. For example, if you had 3 newtons right there is in between those 2. Or, include it in the boundaries. Is part of that. So can be in equilibrium. But for example, if you had 4 newtons, 12 newtons, and 20 newtons, you know, if you looked at any two, let's say I just choose these two, what's the biggest they could add up to? Well, they could add up to, they would make a resultant of, 32 newtons if they were both going the same way. If they're going in the opposite direction, they would have a resultant of 8 newtons. So is it possible that a 4 Newton force balance out these two that have a resultant between 8 newtons and 32 newtons? And the answer is no. 4 newtons cannot balance these two out because the smallest these two could be is 8 newtons. So there's no way a 4 Newton force could balance them out. So since 4 is not in between 8 and 32, this is not a situation where the forces are in equilibrium. Now, sometimes the vectors are velocity vectors, and you have to find the resultant. And a classic example of that are river problems. Good old river problems. And basically, there's two situations. One where the river is flowing this way, and you have some sort of boat or something, and it's headed straight across. And let's say it's headed straight across at 3 meters per second, and the river velocity is 4 meters per second. And let's say they tell you that the river is 100 meters wide. Of course, you could be asked to find the resultant velocity. And if you were asked to find the resultant velocity, you would take the two velocity vectors and put them head to tail. 3 meters per second, and then 4 meters per second. And then the resultant would be 5 meters per second. And then if you use inverse tangent, I think this angle in here turns out to be 53 degrees. So the resultant velocity would be 5 meters per second, 53 degrees clockwise from the positive x-axis. But sometimes the question just asks, hey, how much time would it take for that boat to cross the river? And if you wanted to know the time across, instead of using the resultant velocity and this actual resultant displacement, which you'd have to figure out, it's so much easier just to realize that this blue vector right here, the 4 meters per second, the river, has no effect on how fast the boat is going this way across the river. So if you want to know the time across, just use v bar equals x over t. And for the velocity, use the velocity straight across. And for the displacement x, use the distance straight across, and then solve for that time. And what would that come out to? 100 divided by 3, which would be what? 33.3 seconds. And that's how long it would take the boat to go if there wasn't any river current, or if there was a river current. So now that we've discussed vectors and how to add those up, and we discussed the motion formulas, we reached one of the most powerful formulas, of the first quarter, and that is Newton's second law. Because Newton's second law is the big bridge. Over here you have the motion stuff. I'm just going to quickly jot this down. V bar equals x over t, a equals delta v over t, v bar equals vi plus df over 2, and then over, what do we have here? X equals vit plus 1/2 at squared, vf squared equals vi squared plus 2ax. You have your motion stuff over here, and then over here you have your forces stuff, where, here you have F1 and F2, and since they're both going the same way, the net force, you just add them up, F1 plus F2, and then of course if F1 and F2 are at right angles, you'd have to do F net is equal to the square root of F1 squared plus F2 squared. And then of course if F1 and F2 were in opposite directions, then basically F net is equal to F1 minus F2. So now that we have the vector stuff over here, the big bridge that connects these is Newton's second law. And that is F net equals n times a. Notice over here you have motion terms that have the a in it. A. And over here you have the F net terms. F net, F net, F net. So sometimes you have to start off by doing a vector problem and getting the net force, putting the net force on the bridge here to get the acceleration, and then bring the acceleration over here to solve a motion problem. Other times you have to solve a motion problem to get the acceleration. You put the acceleration in here to get the net force, and then you come and use the net force to figure out one of the individual forces. So one of the biggest strategies, if you're looking at a problem and you're trying to figure out how to do it, strategy number 1, draw a free body diagram showing all of the forces acting on the object. Number 2, apply that powerful formula. F net equals m times a. And then realize that that a right there might have to come from a motion problem, and that F net might come from a vector problem. Okay. This is popularly applied with inclined planes. And basically, an inclined plane is just a ramp, and you're usually given theta down here in the corner, and you're given a certain mass. And if you're asked to draw a free body diagram showing all of them, and perhaps you're given the coefficient of friction, mu sub s is 0.5, mu sub k is 0.3, and we'll circle back and talk more about that in a second. But that indicates that there really is friction there. What you would want to do is draw the free body diagram first. Now you have to be careful. When you draw a free body diagram, if you're asked to draw a free body diagram, especially the other physics teachers, if they're grading your papers, they're very fussy about this. If they say, draw a free body diagram of the object, then originally, in that first diagram, don't show any component forces. Because other teachers treat that as being like redundant. So don't show any component forces, only show whole forces. So for example, if you're going to draw the free body diagram of this, you have the whole weight force. You could call it Fg, or you could go straight to calling it m times g. You got the normal force holding out underneath the ramp this way. And if the object wants to slide down the ramp, there's also a friction force acting this way. So those are the only three forces acting on that object. Now, so I start off with this diagram. A second diagram, you might want to replace Fg with its component forces. That weight force, which always acts straight down towards the center of the earth, could be broken down into parts. Part of that weight force pulls the object down the ramp. I personally call that Fg parallel. Part of that weight force squeezes the object straight in. I personally call that Fg perpendicular with the upside down T. You need to memorize how to calculate those components. You could draw a little right triangle and figure it out, but you don't have time to do that. You want to know immediately Fg parallel is going to equal to mg sine of theta. Fg perpendicular is going to equal mg cosine of theta. To memorize which one is which, just recall the old expression, sine makes it slide, because Fg parallel pulls it down the ramp. Cosine keeps it close, because it pulls the object in close.
Where is data for the components of Fg?
Well, back in this diagram here, if you drew your Fg parallel and Fg perpendicular,
It's like right by the mast, right? It's not by that.
This is FG perpendicular. That's FG parallel. But since they're components, if you pick FG parallel up and put it in head to tail form with FG perpendicular and you put it down here, FG perpendicular and FG parallel make a right angle right there. And if you look at the trig, or I should say the geometry, if that's theta, this top angle right here is theta. Theta is always the angle between FG and FG perpendicular. And then you could use SOHCAHTOA to figure out, oh, FG parallel is equal to FG sine theta, and FG perpendicular is equal to FG cosine theta. But, you know, instead of making that triangle and figuring it out, I say, hey, boom, just have these two memorized. So, strategy, draw a free body diagram. Second step, apply. Fnet equals MA. So basically, if I look at this direction right here, 1, 1, 1, 1, that direction, and I apply Fnet equals M times A. Some physics teachers write it, sum of the forces equals M times A. Either or is fine. Well, I know that object wants to slide down the ramp, so I'm going to make this direction my positive direction. So if the object wants to slide down this way, I know that my FG parallel is going to be bigger than my F sub F. So therefore, the sum of the forces, vector problem, they're in the opposite direction, is going to be FG parallel minus the force of friction equals M times A. And then for FG parallel, you can make the substitution mg sine theta. And for the force of friction, you can make the substitution mu times the normal force. But on an inclined plane, the normal force is not equal to the whole weight force, it's equal to FG perpendicular. So if I was going to substitute for the normal force, since the normal force equals FG perpendicular on a ramp, I substitute in for the normal force mg cosine of theta. And then usually I'd be given enough information to solve for one of the variables. So then you go on and solve for one of the variables.
Which view would you use?
It all depends. If the object was definitely sliding and you had an acceleration, then you'd use mu sub k. If the object was not sliding and it was like hung up there at rest, then the acceleration would be 0, and then you'd be dealing with static friction. Yes. Right. Right. All right. So basically, this brings us to projectile motion. And there's two main problems that you want to be able to do. A projectile shot horizontally from the top of a cliff, like this, where you're given that initial velocity and you want to predict, like, hey, how far out here does it go and whatnot. And then the other type of problem you want to be able to do is the problem where it's down on the ground and it's shot up at an angle. And you want to calculate, like, hey, how high does it go and how far does it go? So these are the two standard type of problems that you have to deal with. Let's deal with the top one first. So with all projectile motion problems, you always set up a chart. And every piece of data and every formula should be written either on one side or the other side. The one side represents the horizontal motion, the other side represents the vertical motion. Both of these motions are occurring simultaneously, but yet they act independently because they're at right angles to each other. And for every single projectile motion problem, you always start off by listing the acceleration in the x direction as being 0 meters per second squared, and the acceleration in the y direction is always going to be negative 10 meters per second squared, or you could say negative g if you're going to solve the whole thing in terms of symbols. Since we're just dealing here with symbols, I'm just going to call it negative g. The next thing you want to list in both cases is the initial velocity. What is the initial velocity in the x direction? What is the initial velocity in the y direction? Well, many times this is given right here. This vi right here is the initial velocity horizontally. So, that's that blue v sub I over there. This velocity here. But in the y direction, initially, the projectile is only going horizontally for the initial moment that it's released. Of course, the second moment in time, it starts to go down because gravity is going to start pulling it down. But the first instant of time, it's only going horizontally. So this here is 0 meters per second. And of course, when x sub y equals h, at the very beginning, and then at the very end, xx max, or I should say xx equals xx max at the end. Usually you're given enough information in one of the columns to figure out the time. And then once you get the time in that column, you take the time over to the other side. Usually, the formula that you use on both sides is x equals vit plus 1/2 at squared. Oh, yes. That should be negative h. Thank you. Because it's going down. vit plus 1/2 at squared. And like I said, usually in one of the columns, you're given enough information to get the time. You solve for the time in that column, and then you take the time over to the other. Usually you solve the y column for the time. So this initial velocity is 0. the x in the y direction right there is going to be negative h, and that's going to equal 1/2 times negative g times t squared. So t here equals the square root of, what is it going to be? 2h over g? And then over here, the acceleration in the x direction is 0, so that term goes. So, the xx max is going to equal the initial velocity, which was given, times the time. But what's the time? Square root 2h over g. Notice the time over here only depends on the height. And if you took this original velocity right here and you tripled it, like made it 3 times faster, well, if you worked out the whole problem over here, look, there's no initial velocity over here in the time. So if you increase that time by a factor of 3, the initial velocity by a factor of 3, the time would still be the same. The time that it takes to land only depends on one thing: the height of the cliff. It doesn't depend on how fast it's shot horizontally. Now, with the other problem, if you want to calculate how high the object goes, the maximum xy, and you want to calculate how far it goes, xx max, you start off the problem the same way. With an XY chart. And just like before, the acceleration in the x direction is 0, and the acceleration in the y direction is negative 10 meters per second squared. Since we're doing the problem in all symbols, that would just be negative g. And then once again, the next thing you want to list is the initial velocity in the x direction and the initial velocity in the y direction. Now, last time that was kind of easy, because basically we just took this velocity given right here, and that was the total x velocity, and the total y velocity was just a 0. But now you have to do a little vector component problem where you have to take this original velocity and break it down into parts. And basically you want to find how fast it's initially going in the x direction and how fast it's initially going in the y direction. And you could either draw a little vector triangle like that and then figure it out using SOHCAHTOA, or you can memorize the fact that Vix is going to equal the whole velocity initial times cosine theta, and Viy is going to equal the whole initial velocity times the sine of theta. So Vix equals the whole initial velocity times cosine theta. VIY is equal to the whole initial velocity times sine of theta. And then our two unknowns, we're trying to figure out how high the object goes and how far it goes. So XX max is a question mark, and XY max is a question mark. And once again, just like before, what I suggest you do is to get both of those displacements, use the great displacement formula. So basically, in both cases, you could use x equals VIT plus 1/2 AT squared. And over here, you could use x equals VIT plus 1/2 AT squared. And notice both sides of the column, you have the acceleration, and you have the initial velocity expression, Same thing with the x column. You have the acceleration, which turns out to be 0, and you have an expression for the initial velocity in the x direction. What's the one thing you need in both sides to bring the problem on home and get those two displacements? The one thing we don't have, time. So if we can just figure out the time, then boom, we're done with the problem. We just substitute in the time, we have everything else we need. So we have to figure out how much time. Now, there's different approaches to these problems. I'm just going to show you, a popular approach. So to get the time, you do an additional calculation. And you consider the vertical velocity on the way up. And we know that the acceleration in the y column is negative g. And we know the initial velocity in the y direction was equal to the initial velocity times sine of theta. But what we also can add to that over there is that the final velocity in the y direction is equal to 0 meters per second. But you got to be careful. That's not the final right before it hits the ground. That's the final on the top. A little reminder there. That's the final on the way up at the top. And therefore, we can find the time on the way up. Sometimes I call that t sub up, the time on the way up. And you can see that that perfectly shouts out the acceleration formula, where you have a equals vf minus vi over t. And if you rearrange and you substitute in, what you end up finding is the time on the way up is equal to what this simplifies out to be. You have negative vi sine theta over negative g. The top originally is going to be 0 minus vi sine theta, because the final velocity is 0. But I just dropped the 0, so it's just negative vi sine theta. And of course, you got a negative over a negative, so they become positive. So the time up just becomes vi sine theta over g. Now, when you go to calculate these distances over here, when you're going to get x in the y direction maximum, you get that height, we know that that equals to vi in the y direction, so this is going to be vi sine theta multiplied by time, but you're only going to use the time up. And that time up turned out to be equal to, what was that time up? I sine theta over G plus 1/2 times negative G times that time up, dI sine theta over G quantity squared. So that gives you your expression for xy max. You only use time up. So back over here, I'm going to put in a little time up. But when you go to figure out the xx max over here, of course, the acceleration in the x direction is 0. You have vi in the x direction, which is just vi cosine theta, times, but now you're going to use the total time, t total. So that's going to be 2 times the time up, so that's going to be times 2 times vi sine theta all over G. Now, if we straighten that up, we clean that up, you see we have a vi squared, and then we have 2 sine theta cosine theta. I don't know if you can see that because of the way I wrote it, but it's 2 times sine of theta times cosine theta. But there's a trig identity that says that that's equal to the sine of 2 theta. 2 sine theta cosine theta, and then that whole thing divided by G. Now, this answer on the right is technically a correct answer. And of course, if you had numbers, you could just plug it in and crunch it out. But with symbols, it's kind of a bear to clean that up. So a little shortcut trick is sometimes to get the xy max, instead of having to do 2 terms, because notice, neither of the terms drop out. This term doesn't drop out, nor does that term drop out. So there's 2 tricks to get xy max. Basically, you can consider the way down instead of the way up, and that makes things a lot easier. So on the way down, we know the acceleration in the y direction is equal to negative g. And we know that, the initial velocity in the y direction on the way down, well, on the way down, what's up with that? Right here, on the way down, what's going to be the initial velocity in the y direction? 0. And we know that the time on the way down is equal to the time on the way up. And that's equal to, what was that? vi sine theta over G. And we're looking for xx max. So if we, xy max. If we put in here, what do we end up getting? We have vit plus 1/2 at squared. Vi is going to be 0, though. You see how that crosses out? And then we get 1/2 times negative g, because it's on its way down, but this is actually a negative there, and those negatives cancel out, times t squared, which is vi sine theta over g. This whole thing gets squared, and it's easy to simplify that up. X of y ends up equaling, what is that going to be? Vi squared sine squared theta all over what? 2g. If you clean that up. Finally, a third way of getting xy max, that's the max, that's the height right there, is just to use the no time formula. So a third way to get xy max is, of course, always considering the vertical, use the no time formula. Even on the way up. On the way up, we know the initial, well, of course, we always write the acceleration in the y direction is negative g. And the initial velocity in the y direction is equal to vi sine theta. And the final velocity on the top is equal to 0 at the top. And we're trying to figure out how high it goes. X, y max. Well, notice that shouts out the no time formula. So you could just use vf squared equals vi squared plus 2ax. So y. And of course, the final velocity on the way up is 0. So 0 equals the initial velocity squared, vi sine theta over g, squared, plus 2 times negative g times x, y max. And if you solve that for x, y max, you get the same thing you got on the last page, right here. All right, so some facts you need to know about these type problems. When theta equals 45 degrees, the object goes the farthest. That means horizontally. The range is the greatest. It's tricky because in physics, range is horizontal as opposed in math. When theta is 9 degrees, the object is shot straight up. Object goes the highest. And object is in the air the longest. So at 45 degrees, the object goes the farthest. At 90 degrees, it goes the highest, and it's in the air the longest. Okay, next, circular motion. If the object's going in uniform circular motion, you need to know that the velocity is always tangent to the circle. The acceleration is centripetal towards the center. And the force acting on the object is centripetal towards the center of the circle. And then the formulas to calculate those. To get that tangential velocity, it's the circumference divided by the period, where r is the radius of the circle, and t is the time for it to go all the way around once. The centripetal acceleration is equal to that velocity that you just got squared divided by the radius, and the centripetal force is equal to the mass of the object that's going in the circle times the centripetal acceleration. Those are the three circular motion formulas. That you have to know. In this case, r is the radius for the center of the circle. Well,
yeah, isn't there a formula where it's like r plus b?
yeah. Yeah, so if this is M1 and this is R1, some planet, and the planet has a radius R1, and then you have some satellite that's in a circular path and it's a distance h above the surface. Well, in that formula, v equals 2 pi r over t, and in that formula, a sub c equals v squared over r. Well, r, capital R in these two formulas, remember, is the radius of the circular path that the object is going in. So if this is the circle, and this is the center of the circle, well, what's the radius of that circle? plus
Oh, the larger one is
plus h. So for the satellite, this r right there and that r right there would be the sum of the radius of the planet plus the height above it.
sorry, that's the distance from the center.
And that's the distance from the center. That circle's not drawn very nice.
But they usually ask it from center or from surface.
All depends on the problem. Just read it carefully. All right, so with those formulas, you can combine them. So, for example, if v equals 2 pi r over t, and a sub c equals v squared over r, and f sub c equals m times a sub c, of course, you could take this a sub c, substitute in the third one, and you could have f sub c equals m v squared over r. But then in that, you could substitute the first formula, and you could say f sub c is equal to m times 2 pi r over t squared, because that's what the velocity is, all over r. And if you simplify that, what would you end up getting? M times 4 pi squared r over t squared. So there's other versions of that centripetal force formula. I say, don't worry about that. Just memorize these three right here. You know how to substitute in. You know, you could just bring them up if you have to.
So
Yeah.
why would it be over t squared and not t? Like, doesn't one of the t squared cancel out?
Well, v right here is equal to this whole thing.
Yeah.
So right here, see where that v gets squared? So what is v? I put in this parentheses, the whole thing, top and bottom, gets squared.
Yeah, and then it becomes, I thought, 4 pi squared, r squared over t squared, and then both, like 1 r gets canceled, 1 t gets canceled.
What does the t get canceled with? There's no. Okay. Yeah, there's nothing for the t to get canceled.
And then, okay.
There's only an r down here, which ends up canceling with one of the r's. That's why it's just r here, not r squared. But there's nothing else with the t. So then, the next thing you have to ask yourself, the question is, what is providing the centripetal force? On your free body diagrams, you never draw the centripetal force as one of the forces that are actually there. The centripetal force, that's a generic name for whatever physical force is actually there providing the centripetal force. So I'm just going to make a note, on free body diagram, never draw F net, nor draw F sub c. F net and F sub c are like these labels for like the overall effect in a certain direction. And what we're trying to figure out is like what physical forces are going to be there that provide the centripetal force. So basically there's always three examples that come to mind. And that is one, like if you have a stone on a string and the stone is being twirled around. Well, in that case, it's going to be a tension force, F sub t, or just t if you want to call it. And basically, when you write F sub c equals m times a sub c, and you say, hey, what's providing the centripetal force? Well, it's going to be a tension force. The tension in the string provides the centripetal force. The next example is a car going around a circular path. The actual force providing the centripetal force, believe it or not, is a sideways static friction force. This is an overhead view of a car. So this time when you go to write your, hey, F sub c equals m times a sub c, what's providing the centripetal force? Well, there's no string attached to the car. It's actually a sideways static friction force providing the centripetal force. And then, of course, from there you could substitute mu times F sub n, and then you could just keep on going down with the substitution. So sometimes it's a string, and the tension in the string provides the centripetal force. Sometimes it's a sideways friction force. And finally, sometimes it's a gravitational force where you have M1 and you have M2. And M2 could be a natural or artificial satellite, and M2 is orbiting M1. And when it's going in that circular path, you know there's a centripetal force, but you never label centripetal force on the three-body diagram. You label the actual force that's there. And in this case, it's the force due to gravity providing that centripetal force. So when you go to write F sub c equals m times a sub c, it's going to be F sub g equals m v squared over r. Which g? Okay, in those formulas, Fg equals m times g, and potential energy due to gravity equals mgh. If you're dealing with the surface of the Earth, g is always positive 10 in both those formulas. That's why with the projectile motion problems, when the acceleration was negative 10, I called it negative g. And then, of course, this force due to gravity is equal to big G m1, m2, all over the distance to the center squared. And now you got to be careful. Which m is this? Well, this is m2. This is the satellite or the planet or whatever is out there going in the circle. So what's providing the centripetal force? The force due to gravity. What's the force due to gravity equal to? Fg m1 m2 over r squared. So with this special case, folks, there's like 3 formulas for calculating this force right here. That force is equal to m2 v squared over r. That force is equal to g m1 m2 over r squared. And that force is also equal to m2 times the acceleration due to gravity out there. And since those 3 are equal, you could choose to set any of these 3 right-hand sides and set them equal to each other. I just memorized those 3 force formulas for a planet orbiting another star or something. Because there are 2 more formulas that you have to know. So you either have to memorize them or you could derive them. You need to know the formula for the tangential velocity. So basically what I do is I just take the top 2 equations and set them equal to each other. So I have m2 v squared over r equals g m1 m2 over r squared. And then the m2's of course cancel out. Wah, 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 wah. This r cancels with one of those r's. And you're left with that tangential velocity is equal to the square root of g, the universal gravitational constant, times m1 over r1. The other formula you need to know is, hey, out here, what's the acceleration due to gravity? We just found, like, hey, what's the tangential velocity? Now, out here, hey, what's the acceleration due to gravity? Well, it's not negative 10 meters per second squared, way out there. So to get the acceleration due to gravity formula, I take the bottom 2 equations and set them equal to each other. And you have m2g equals big G m1 m2 over r squared. And then notice the m2's cancel out. And it turns out that the acceleration due to gravity up there is just equal to big G m1 over r squared. Now, if you want to know the acceleration due to gravity way out here, then basically your r would be from here to the center of that planet right there. Wah, wah, wah. That's that r right there. However, sometimes you're asked to calculate the acceleration due to gravity on the surface of a planet. You're asked, hey, what's the acceleration due to gravity right here on the surface? Well, if you're going to use that, then you would use the radius of the planet. I'll call r sub p, the radius of the planet. So if you want to get the acceleration due to gravity on the surface, then you just use the radius of the planet squared. you want to know the acceleration due to gravity way out here where the satellite is, use this big R. We said before, that big R sometimes is referred to as the radius of the planet plus the height. If you want to know the acceleration due to gravity right on the surface, then just use the radius of the planet right there. How you guys doing? Is it all coming back to you? Like, work, power, energy, and momentum.
Wait, really quick.
Yep.
Would they give you what the big G equals in the
Yes.
question?
Yes.
So you
Yes.
don't even memorize that?
Correct. Okay. Okay, work, power, and energy. Recall the work formula is equal to the force times the distance the object moves times the cosine of theta, where theta is the angle between the direction of the force and the direction of the motion. So if you have an object and the object is moving this way, whoopsie, that's its direction of its velocity, and there's some force acting over this way, theta is the angle between the force and the direction that the object is moving. Now notice, if the object is moving this way, and you have a force that's acting this way, theta would be 90 degrees, and if you put 90 degrees in for that cosine function, the cosine of 90 turns out to be 0. So in this situation here, that force isn't doing any work. This comes up all the time with circular motion. With circular motion, look, the direction of the object is always tangent. The direction of the force is always centripetal. What's the angle between the direction that the object is moving and the direction of the force? It's always 90 degrees. So it's very common to ask the question, hey, how much work does that centripetal force do? And the answer is, centripetal force always does 0 work because theta is equal to 90 degrees. Now power is how fast the work gets done. So it's work divided by time. However, work in general is the force times the distance over time, assuming that theta is equal to 0. And notice I can rewrite that one more time, force times distance over time. And then you might recognize that distance over time, that's average velocity. So a more obscure power formula is force times average velocity. Either way, power comes out in joules per second, which is equal to watts. this leads us to the big work energy theorem. Which is the kinetic energy at one point plus the potential energy due to gravity at that point plus the potential energy in a spring at that point plus any non-conservative work done is equal to the kinetic energy at another point plus the potential energy at the other point plus any stored up potential energy in a spring at that other point. Now, of course, you need to know how to calculate all those terms. Kinetic energy is 1/2 the mass times velocity squared. Potential energy due to gravity is equal to mgh. And the potential energy stored in a spring is equal to 1/2 kx squared. And then, of course, your work formula is, the FD cosine theta. But you got to remember, non-conservative work is never, that never includes the work done by the force due to gravity, nor does it include the work done by the force of the spring. Never includes work done by the force due to gravity, nor the work done by the force of the spring. The non-conservative work, includes the work done by maybe an applied force and the work done by the force of friction. And usually there's formulas that, it simplifies down. 9 times out of 10, there isn't any non-conservative work, and there isn't any springs involved. So if there isn't any non-conservative work, and if there isn't any springs, it simplifies down. So if the non-conservative work equals 0, and potential energy in a spring, initial and final equals 0, then that big formula boils down to the initial kinetic energy plus the initial gravitational potential energy equals the final kinetic energy plus the final potential energy due to gravity. It all depends on the problem, but it usually, you never usually use every single term in this formula. Usually a majority of them are going to cancel out. They're not going to be involved. So anytime you're dealing with a problem where you could see that there are 2 points, a point here and a point here, and maybe over here there's altitude, and maybe over here there's a compressed spring, and maybe over here it's moving with a velocity, that shouts out, use that big work energy theorem. When you see a problem that has, something moving from one place to another, and it has potential energy or kinetic energy or spring energy at one place, that shouts out, hey, go back and apply this big formula. Yeah. Yeah, the force of the spring. Because the work done by the force due to gravity, that's taken care of by these 2 terms. And the work done by the force of the spring, that's taken care of by these 2 terms. Now the tricky thing is, if you are ever asked to calculate these, if you're ever asked to calculate these, we're used to using these potential energy terms. So you need to remember that the work done by the force due to gravity is equal to the negative of the change in the potential energy due to gravity. And the work done by the force of the spring is equal to the negative of the change of the potential energy stored in the spring. Now, anytime you have any sort of collision, think conservation of momentum, which basically just says, the sum of all of the objects m times v before the incident equals the sum of all of the objects m times v after the incident. Sometimes the big formula looks like this. M1 V1 plus M2 V2 before the collision equals M1 V1 plus M2 V2 after the collision. Sometimes the two objects stick together. So you have M1 V1 before the collision plus M2 V2 before the collision. If they stick together, you have M1 plus M2 stuck together times their final velocity. They stick together. Now, if it's an elastic collision, objects bounce off of each other and no kinetic energy is lost. So for elastic collisions only, you have conservation of kinetic energy. Again, that's for elastic collisions only. So basically, what that boils down to is like, 1/2 m1 v1 squared of the first object plus 1/2 m2 v2 squared of the second object before the incident equals 1/2 m1 v1 squared plus 1/2 m2 v2 squared after the collision. Now, some people put in extra subscripts like initial, final. If that helps you, great. If that confuses you, just remember what they are. You're welcome. Now, impulse is equal to force times time, or impulse is equal to change in momentum. Momentum, on the other hand, is equal to mass times velocity. So these are the three key formulas with impulse and momentum. You're 1, 2, 3. Now this formula here, though, could be written, written a few different ways. J is force times time, and change in momentum is the mass times the final velocity minus the mass times the initial velocity. So this is just an expanded version of impulse equals change in momentum. And I think I'm going to stop here.